Assalamu alaikum. Hello everyone, and thank you for having me today. I am truly honored to join you virtually from the United States, even though I wish I could be there with you in person. So my name is Ameni MKAOUAR, and I am a postdoctoral researcher at NASA, working through the University of Maryland, Baltimore County. I'm originally from Tunisia, so it's especially meaningful for me to be part of this conference in Algeria. It feels like being home. So today I want to share a bit about my journey from Tunisia to NASA and also talk about the work we are doing to simulate and fuse spaceborne data from LiDAR and stereo imaging system. So more than just a research talk, I hope today's presentation inspires some of you to pursue your own paths in science, in technology and exploration. And let's get started. So this photo was taken at AGU, the American Geophysical Union conference, where I had the opportunity to present my research alongside scientists from all over the world. For me, this wasn't just about science, it was a moment of reflection and how far one can come. And I was born and raised in Tunisia. Like many of you, I studied hard. I was curious about the world and dreaming big, even when it didn't always feel possible. And yet, step by step, with the right mentors, with persistence and a lot of learning, I ended up here working on NASA projects, collaborating internationally, and trying to contribute to global science. You don't need to be born in Silicon Valley to work on space science. What you need is curiosity, perseverance, and a purpose. If there is one thing I want you to take from this moment, is this: your background is your strength, and if I could do it, so you can, and I hope many of you do even more. So yes, that journey from Tunisia to NASA has been, it wasn't easy, but it's not just about where I've come from, it's about what I am working towards. The work is changing fast. So climate, forest, water, coastlines, all shifting in ways that affect every single one of us, and that's where my work at NASA comes. I've been part of a team contributing to one of NASA's key science priorities, which is the surface topography and vegetation, the STV target observable. It's not just about capturing stunning images from space, it's about understanding the planet's surface in 3D and how it's evolving in response to both natural processes and human activity. So let me introduce you to the vision behind STV. So this program is part of the broader effort laid out in NASA's 2017-2027 decadal survey, where scientists come together to define the most urgent Earth science questions we need to answer in the next decade. One of those priorities is understanding how Earth's surface and the vegetation that grows on it is changing over time. That's exactly what STV is designing to do. So, but STV doesn't just ask what does the Earth's surface look like. It goes further, asking why is it changing, and how are forests, glaciers, coastlines, and landscape evolving in response to climate and human activity and the natural forces. So to do this, STV uses cutting-edge satellite technology to capture detailed 3D information, not just of the land surface, but also about the structure of vegetation and even bathymetry, and this is for laying the ground for the next generation of satellites that can help us model climate change, track carbon storage, and predict natural disasters. And of course, manage ecosystem more effectively. To achieve the ambitious goals of STV, so NASA relies on advanced Earth observation technologies, and two of the most powerful technologies are LiDAR and stereometry. So let's start with LiDAR. So LiDAR stands for light detection and ranging. I think that you can imagine it like this. So imagine pointing a flashlight at the ground and timing how long it takes for the light to bounce back. That's the basic idea. So LiDAR uses laser pulses instead of regular light, and these lasers are sent from satellite, airplane, or drones, and by precisely measuring how long the laser takes to return, we can determine how far the ground or the vegetation is from the sensor. So doing this millions of times across a landscape, and you get a high resolution 3D map, not just of the background surface, but also of what's above it, like trees, buildings, etc. So here you can see an example of the Jedi, or here the Jedi is one of the powerful LiDAR, spaceborne LiDAR sensor, which can see through the canopy. The Jedi stands for Global Ecosystem Dynamic Investigation, is mounted on the International Space Station and collect data globally to measure forest height and structure. This is really critical for understanding how much carbon is stored in forests and how forests are changing. This is an example of a vertical profile of Jedi track over forest. So Jedi is a full waveform LiDAR. And another example here is the ISAT-2, which is another type of LiDAR, which is a photon counting LiDAR to map both land and ice with centimeter level accuracy. So it's important for tracking changes in snow, in glaciers, sea ice, and surface elevation. So that's LiDAR, and it gives us structure, precision, and ability to see what's hidden beneath the surface. But what if we want wide coverage and very high resolution images? So this is a shortcoming of LiDAR, which give us sparse measurements, especially from laser altimetry. That's where our next technology comes in, which is the stereometry. To explain this, imagine you are looking at something with both of your eyes. Your brain combines the two views to see depth and create a 3D image. In remote sensing, stereo images works in a similar way. So a satellite captures two images of the same area from slightly different angles, just like how each of your eyes sees a slightly different perspectives. By comparing these two views, we can measure the height of objects like trees or buildings and build 3D models of the landscape. One example of this is the NASA Worldview satellite. They take high-resolution images from space, which we can then use to create detailed maps for things like urban planning, disaster responses, and environmental monitoring. Now that we have introduced stereoimagery, let's talk about the three important models used to describe the Earth's surface and vegetation, which are the DSM, the DTM, and the canopy high model. So the DSM is the digital surface model. This represents the elevation of the Earth's surface, including both the ground and anything on top of it, like trees, buildings, and mountains. It's like taking a snapshot of everything above the ground. The DTM is the digital terrain model, and it is similar to the DSM, but it removes all the vegetation and man-made structures to show only the bare ground surface. Think of it like peeling off the top layer. And the canopy is the canopy high model shows the height of vegetation like trees. It is created by subtracting the DTM from the DSM, giving us a model that focuses only on the canopy. So how does stereoimagery help here? So stereo is used to create these models by comparing two satellite images taken from different angles. By looking at the difference in how objects appear from different points of view, we can measure their elevation, height, and shapes, which are essential for building those models. So in short, stereo lets us understand the height of both the ground and the object on it with great details. Let's move to the next slide. On this slide, we can see a comparison of the key features of LiDAR and stereoimagery, focusing on coverage, resolution, vertical structure, and other important characteristics. So by fusing LiDAR and stereo, we can combine the strength of both. For example, LiDAR gives us accurate vertical measurement, especially for ground and structure, and stereo images provide wide coverage and satellited and detailed surface textures. So together they allow us to enhance vertical accuracy in digital surface models and DTMs by filling in gaps left by either system individually. And even with the fusion, here we are highlighting some of the key challenges that we face when working with stereo and LiDAR for accurate Earth surface modeling. First, the limited stereo acquisition geometry. I mean, the angles from which we acquire stereo images may not be optimal for capturing all features, especially in complex terrain. The pointing and geolocation error from LiDAR, I mean the small errors in the sensor position that can lead to errors in how we map our Earth surface, and the vegetation change. I mean the season, leaf on, leaf off season, that the presence and absence of leaves highly affect the both quality of data, and also no existence of truth or data sets to let us testing all the conditions that we need or that we face in real life. So to address these challenges, we developed a simulation pipeline. So this pipeline combines real LiDAR data, and those data are acquired from airplane, which are considered very precise data, with 3D radiative transfer modeling, which is the interaction between the light and the vegetation surface. This will be done using the DART software, which stands for the Discrete Anisotropic Radiative Transfer Model. Is a radiative transfer model developed at CESBU, Toulouse, France, since 1993. And by using DART, we simulate how stereo imagery and LiDAR would behave under various conditions, allowing us to explore different sensor geometries, different terrain type, and all of this is without having a real world data that may that may be incomplete or inconsistent or having how to say inaccuracies due to different parameters. So our method involves 3 key steps to simulate and analyze the fusion of stereo images and LiDAR data for improved surface and vegetation modeling. So the first step is the scene reconstruction using the PVLAD model. So this model was developed to let's say to estimate leaf area density from airborne LiDAR data, and then reconstruct the scene in voxels of size, for example, 1 meter or 0.5 meter. This scene will be incorporated in Dart for the simulation. So this is a detailed 3D representation of the forest structure, and this step will allow us to build a solid foundation of the terrain and vegetation, which is crucial for our accurate simulation. The next step is the incorporation into Dart for simulation. In this step, we integrate the reconstructed scene into Dart, and here Dart, based on the RT modeling, it will enable us to simulate stereo images at different acquisition angles and scene angles with realistic sensors parameters, both for images and for LiDAR. So by adjusting these variables, we create synthetic images that mimic real-world conditions, accounting for sensors geometry, lighting, and terrain characteristics. And for the third step, we simulate different types of LiDAR data, including full waveform, photon counting, and more, alongside the stereo images. This simultaneous simulation helps us evaluate how these different data types behave under the same condition and how their fusion can enhance vertical accuracy and surface modeling. Next, we move on to the last step of the digital surface model derivation. And to achieve this, you will be using the NASA stereo pipeline. This pipeline is a proven tool for processing stereo images, and it's capable of generating highly accurate DSM from satellite images, which are captured at different angles. So using the stereo pipeline, we will extract detailed 3D models of the Earth's surface, focusing on elevation and terrain features. This will give us high-resolution data on the surface structure, which is essential for understanding vegetation and topography. An important advantage of the NASA stereo pipeline is that it is an open source tool, meaning it is freely available for use and modification by the scientific community. This makes it an accessible and collaborative tool, enabling researchers around the world to contribute to improving and refining the pipeline, as well as applying it to a wide range of remote sensing applications. Once we have our GSMs, the next step is to fuse them with LiDAR data by combining the detailed topography from the GSMs with the precise vertical measurements provided by LiDAR. So we aim to improve the overall model accuracy, especially in capturing vertical features like tree height, canopy density, and terrain slopes. So this fusion will enhance our understanding of the Earth's surface and allow us to respond more effectively to key scientific and environmental questions. While the fusion of stereo and LiDAR data holds great potential, it's important to note that the work is still ongoing. In this presentation, I will be showing you preliminary results of how this fusion could work, but we are still in the process of conducting additional experiments with different configuration and at various study sites. These experiments will help refine the methodology and enhance the accuracy of our results. The journey is far from complete, and there is much more to explore in order to fully unlock the potential of stereo LiDAR fusion. Those are results. And in this slide we have a visualization of the circ site marked by the white square in the left image, with the Jedi and ISA 2 tracks in red and blue respectively. In this slide we also include the DSM derived from J-Light LiDAR. Here it will be as a reference or as a truth for us for dataset comparison. The plot in the middle illustrates the configuration of the viewing and sun angles for the configuration we are simulating. We are also showing an example of the simulated images at different viewing angles from DART, highlighting how changes in acquisition geometry can impact the images. Here, please take note of how the simulated images maintain their fidelity to their reality despite varying acquisition angles. Also, you can observe the level of details in the simulated images from DART. These images are not only closely looks like real-world data, but also capture a high level of structural details. This makes them suitable for use in training, for example, deep learning models, or can be used in other applications. So the level of details in the simulated images can be leveraged to create robust datasets for different applications. Here we can compare the DSMs derived from different convergence angles to the truth DSM from LiDAR, which serves as our reference. So these map, we can see here that these maps allows us to visually assess the accuracy of the simulated DSMs, showing us how closely they match to the LiDAR derived truth model. So the goal is to demonstrate the accuracy of our simulated DSMs. Now let's analyze the DSMs derived from the stereo pairs with different convergence angles. We observed an important trend here for smaller convergence angles. They are generally provide the most accurate canopy surface elevation as compared to the J-Light DSMs, which is our reference. And on the other hand, the stereo pairs with wider convergence angles, for example, those one, or we can focus on the wider one, they show lower noise, particularly in the non-forest area when compared to the J-Light DSM. So this highlights the strength and trade-offs of using different viewing geometry for DSM generation, and its important insights as we continue to refine our fusion process for more accurate and precise terrain modeling. Here are the residuals, or the difference map between the derived DSMs and the reference LiDAR, and we can see that the same observations are valid here. In this slide, we are looking at two vertical profiles, the Jedi profile and the ISA2 profile, and compare it with the elevation derived from the simulated DSMs sampled at each footprint level. We have also included statistical metrics like the here we have the bias, the standard deviation, and RMSE for the DSM derived elevation when compared to the reference LiDAR elevation. As you can see, the Jedi profile shows closer agreement with the LiDAR elevation, particularly in area with dense vegetation. This is likely because the JEDI mission was specifically designed for measuring vegetation, providing more accurate results in those areas. In contrast, the ISAT-2 profile shows some deviations, likely due to its broader mission focus on ice measurement. Now, when comparing the DSMs derived from stereo images with LiDAR profile, we observe that stereo-derived DSM with smaller convergence angles provide more accurate elevation estimates, and this is especially important in vegetation because a small convergence angle have the ability to penetrate more in the vegetation. Looking at the elevation values sampled at the footprint location for JEDI and ISAT-2, we found that the stereo-derived TSMs show closer alignment with the relative high of like 90% is not it's not reaching the top of canopy, which inform us that the fusion can enhance the elevation of the DSMs and make it more accurate. To conclude, the fusion of stereo imagery and LiDAR has the potential to revolutionize our understanding of Earth's surface and vegetation structure, providing highly accurate and detailed elevation data. By exploring the relationship between convergence angles and DSM accuracy, we are moving toward refining stereo LiDAR fusion methods for improved canopy and terrain measurements. This will play an important role in advancing NASA's surface topography and vegetation program, helping us addressing global challenges like climate change, carbon, and natural hazards. So future work will focus on optimizing fusion models, expanding to various forest types, and refining the method for more diverse and accurate environment monitoring. The results we have seen so far underscore the promise of this technology for advancing Earth science. This research has significantly impact for advancing the STV target observable, and moving forward we plan to explore optimal stereo LiDAR fusion model to refine topographic and vegetation structure estimation. And as future work as well will involve extending this approach to a wider range of forest type and densities, particularly mixed and heterogeneous forests across multiple locations within the US. Since I won't be there live with you, I've made it easy for you to ask questions. Just scan this QR code with your phone. It will take you to a simple form where you can drop your thoughts, your questions, your comments, and I will reply to each one after the conference. Thank you.